Right in the heart of the city of Basel, where there is almost no space left for a large construction site, Swiss engineers built a 205-meter-tall concrete tower with 50 floors, making it the tallest building in Switzerland. But behind this skyline-breaking record was an intense battle against both space limitations and engineering challenges. A 20-meter-deep foundation pit had to be excavated in the middle of a dense urban area. A 2.5-meter-thick concrete-based slab had to be poured within a very short time frame, and the entire structural core of the building was lifted more than 200 meters high, using an automatic climbing formwork system operating continuously, floor by floor. So how was such a narrow construction site in central Basel able to complete the tallest building in Switzerland 2 months ahead of schedule? In today's video, let's join Mandarin Tech to explore one of Switzerland's most impressive construction achievements, Roche Tower 2. When people think of Switzerland, they often picture the peaceful beauty of the majestic Alps or its historic old towns. But right along the scenic banks of the Rhine River in the city of Basel, the Roche Tower 2 project has risen and completely reshaped both the skyline and that perception. With a height of 205 meters and 50 floors, this superstructure officially broke all previous records to become the tallest man-made structure in Switzerland. However, unlike many skyscrapers that rely primarily on steel structures, Roche Tower 2 was built around an extra-thick reinforced concrete core that acts as the main structural backbone supporting the entire tower. Under extremely tight site conditions, engineers were required to deploy an automatic climbing formwork system, organize material deliveries using a just-in-time logistics model, and simulate the entire construction schedule with BIM, Building Information Modeling, starting from the tender stage, making it one of the most remarkable high-rise construction sites in Europe over the past decade. Construction of Roche Tower 2 officially began in early 2017. Before this massive high-rise structure could rise above the ground, engineers first had to excavate a foundation pit up to 20 meters deep in a dense urban environment surrounded by existing buildings. Unlike projects located on open suburban sites where construction space can be expanded more freely, the entire excavation at Roche Tower 2 had to be stabilized step by step. This was achieved using a steel sheet pile retaining system combined with basement levels that had already been constructed down to approximately the middle of the third basement floor. At the same time, a system of board piles was installed beneath the bottom of the excavation as the primary load-bearing foundation, preparing to transfer the full weight of the more than 200-meter-tall tower down into deeper and more stable geological layers below. After the 20-meter deep foundation pit was fully stabilized, the Roche Tower 2 construction site entered one of the most critical phases of the entire project, constructing a mass concrete foundation slab up to 2.5 meters thick, the structural base that supports the entire 205-meter-tall tower above. Instead of functioning as a typical foundation slab that mainly distributes localized structural loads, the foundation slab of Roche Tower 2 was designed to act as a massive gravity concrete block. Working together with the basement structure below, it formed a highly stable platform for the central reinforced concrete core and the entire super tall structure rising above it. An enormous volume of concrete had to be transported and poured within a very short time frame, a decisive factor in ensuring the overall structural stability of the entire building. After the mass concrete foundation slab was completed, the next major structural element to rise was the central reinforced concrete core, the load-bearing backbone of the entire Roche Tower 2. This structural core houses all elevator shafts, staircases, and technical service risers, while also acting as the primary vertical load-resisting system that stabilizes the tower as it rises more than 200 meters above the skyline of Basel. To construct the core within an extremely constrained construction site, engineers deployed an automatic self-climbing formwork system in September 2018, integrating working platforms, hydraulic lifting equipment, and wind protection screens to ensure safe operations at high elevations. Each construction cycle involved installing reinforcement and casting a nearly 4-meter-high section of core wall. Once the concrete reached sufficient strength, the entire formwork system automatically climbed upward to prepare for the next cycle. Thanks to this floor-by-floor climbing construction rhythm, the concrete core of Roche Tower 2 was able to progress continuously at a stable pace. This created a reliable structural spine that allowed the surrounding floor slabs to be installed simultaneously using a just-in-time construction strategy, especially important at a tight city center site in Basel, where on-site material storage space was extremely limited. While the central concrete core continued rising, the floor slabs of Roche Tower 2 were constructed layer by layer around this primary structural axis. At this stage, the tower was no longer developing only in the vertical direction. Instead, it began transforming into a complete three-dimensional high-rise structural system. Located in the center of Basel, the construction site offered almost no space for on-site material storage. As a result, all steel components, reinforcement cages, precast stair units, and technical equipment had to be delivered using a just-in-time logistics strategy, arriving exactly when required and installed immediately after unloading from transport vehicles. This approach ensured continuous progress without overwhelming the already extremely restricted construction footprint. To support work at increasing elevations, the tower cranes were gradually raised in stages as the structure climbed higher. Meanwhile, a high-capacity concrete pumping system with a reach of about 35 meters handled the delivery of concrete to heights approaching 200 meters above ground level. With construction operations fully synchronized, the project achieved a pace of one new floor every 6 to 10 days, an impressive construction speed for a high-rise tower built under the tight spatial constraints of a dense city center site like Roche Tower 2. As Roche Tower 2 rose to around level 21, corresponding to a height of nearly 90 meters, the geometry of the central concrete core underwent its first major structural transition. The cross-section of the core was reduced to optimize load distribution and improve spatial efficiency for the upper floors. However, this also meant that the self-climbing formwork system, which had been operating continuously, had to be partially dismantled and reconfigured at height, dozens of meters above ground. Beyond the geometric adjustment itself, level 21 was designed as a double-height mechanical floor, housing many of the tower's critical building service systems. This significantly increased the complexity of formwork installation, reinforcement placement, and construction sequencing compared with the typical floors below. During this phase, the wind protection screens attached to the climbing formwork system also required reinforcement, with additional bracing members to ensure safe working conditions, as the structure rose higher above the natural wind shielding provided by the surrounding urban environment. Successfully reconfiguring the core geometry at level 21 allowed construction of Roche Tower 2 to continue efficiently at greater elevations above. As the tower later climbed beyond the 160-meter mark, the central concrete core entered its second geometric transition during construction. Similar to the modification carried out at level 21, the cross-section of the core was reduced again according to the structural design, improving load efficiency and reducing the overall self-weight of the tower at higher elevations. As the central concrete core and surrounding floor structures continued rising to higher elevations, several other critical construction activities at Roche Tower 2 were carried out simultaneously on the lower levels. Among these, precast stair units were lifted into position and installed directly inside the structural core using tower cranes with high precision, helping shorten construction time within the extremely constrained workspace of the Basel City Center site. Further down the structure, installation of the building's external facade system also began, gradually forming the protective outer envelope, while the primary structural frame continued advancing upward above. At the same stage, essential technical systems, including elevator components and major MEP equipment, were delivered using a just-in-time logistics approach, allowing subcontractors to coordinate closely with the progress of the main structural works, despite the near-total absence of on-site storage space. By organizing multiple construction operations in parallel, the project team was able to maintain a stable and continuous construction pace throughout the tower's vertical growth phase. Once Roche Tower 2 had passed the complex geometric adjustment stages of its concrete core and the construction system had entered a stable operating phase, the entire site began to move into the most intensive acceleration stage of the project. This was the point at which all construction processes were standardized and optimized to achieve the highest possible efficiency. Thanks to the close coordination between the automatic climbing formwork system, the just-in-time material supply chain, and the synchronization of the structural, mechanical, electrical, and finishing teams, the construction speed increased significantly. The building cycles were continuously shortened, allowing each new floor to be completed in only about 6 to 10 days under optimal operating conditions. Then at the end of October, the automatic climbing formwork system, which had accompanied the central concrete core through hundreds of meters of height, was lifted for the final time, marking the completion of the core construction cycle. Shortly afterward, in early November 2020, the central concrete core was officially completed in full, forming the final load-bearing backbone of the entire tower. Following this important milestone, the last floor slabs were also constructed and fully connected within only about 2 more weeks. The entire main structural system of Roche Tower 2, including the core, floor slabs, and load-bearing frame, was completed by the end of November 2020, around 2 months ahead of the original schedule. But have you ever wondered how Roche Tower 2 could be built on such a tight site right in the middle of Basel, where there was no space to store materials, where every activity was restricted by the surrounding urban environment, and yet the project still finished about 2 months ahead of schedule? The answer did not lie in a single machine or piece of equipment. It lay in a fully integrated digital coordination system, BIM, or Building Information Modeling. In Roche Tower 2, BIM was not simply a 3D model of the building. It was a dynamic digital replica of the entire construction process. The whole project, from the 20-meter deep excavation pit, the massive concrete foundation slab, and the central concrete core, to the automatic climbing formwork system and the façade, was recreated in full within a digital environment using precise technical data. This system allowed engineers to simulate the entire construction sequence before it happened on the actual site. Every potential clash between structural elements, every conflict between the structure and the mechanical and electrical systems, and every issue related to working space could be identified and resolved in the digital model instead of on the real construction site. More importantly, BIM served as a real-time operational control center for the site. In a location like central Basel, where there was no room for material storage, the system helped optimize the entire just-in-time supply chain, ensuring that each component arrived at the right moment, in the right place, and in the correct construction sequence. Thanks to the synchronization between the digital model and the physical site, the entire Roche Tower 2 construction site operated like one unified system, where design, logistics, and construction were continuously connected. This was exactly what allowed the project to achieve such an impressive construction speed and finish around 2 months ahead of schedule. From a 20-meter deep excavation in the middle of Basel to a concrete core rising more than 200 meters into a tightly constrained urban skyline, Roche Tower 2 was not just a high-rise building. It was the result of a powerful combination of precision engineering, tightly organized construction, and one of the most advanced coordination systems in modern building. The entire project, from the massive concrete foundation slab and the automatic climbing formwork system to just-in-time logistics and BIM, operated as one unified system where every possible error was controlled and optimized in real time. It was exactly this level of synchronization that allowed the tower to be completed around 2 months ahead of schedule, despite the extreme limitations of building in the heart of Basel. And that leaves one final question. When engineering, data, and human coordination are combined with this level of precision, how far is the boundary between impossible and possible in modern construction? If you enjoy stories about mega projects and modern construction technology, Do not forget to like, subscribe, and turn on notifications so you do not miss the next videos from Mandarin Tech.